This is the second of the 3-video series on processes and process management. In this video, we will build upon the earlier concept of exceptional control flow that is fundamental to understanding the aspects of process management. These are the contents of this video. We will look into what are processes and how are they created, what is a Fork-Exec model, and how are processes managed. So what is a process and why are we learning about processes? Well, processes are another abstraction in our computer system. The process abstraction provides an interface between the program and the underlying CPU and memory. What do processes have to do with exceptional control flow? Well, the operating system is going to have to use tricks with exceptional control flow to give the illusion to the multiple processes running simultaneously in the system, where each process would think that it is in full control of the CPU and memory resources. This essentially enables multiple processes to run on the same system, and this is how multiple programs share resources. What is a program? It is just a list of instructions, a collection of ordered instructions and the data that forms your code or software application. A processor is the piece of hardware that actually is responsible to run these instructions. And what is a process? A process is an instance of a running program. When you start running a program, you create a process to run that program, which creates a running program instance. So it is very important idea in computer science and it is not the same as a program or a processor. A processor executes instructions and the program is a collection of instructions and data. A process is an instance of a running program in a processor. So a process provides each program with two key abstractions. Logical control flow. Each process has the illusions that it has full control of the CPU as the exclusive use of the CPU, whereas in reality, this is not the case. However, the process gives this abstraction to the program that it has full control of the CPU and that the program has a private virtual address space that gives the illusion to each process that it has control of the entire memory and no one is using that memory. The process gives the programs an illusion that it has an exclusive use of the main memory, whereas in reality, these processes are run concurrently. And we will shortly come to what is concurrency. And these processes are sharing all the resources such as the CPU, the RAM, and all other devices, okay? Why are these illusions important? Well, it simplifies writing programs a lot because you give illusions that the program have complete control of the processor. How are these illusions maintained? Well, firstly, all processes execution are interleaved. That is multitasking. Means it is switching between one process and the other. And secondly, the address space is managed by virtual memory system. So we said that multiple processes are executed concurrently. The question then would be, what is concurrency? Two processes are said to be running concurrently if their instructions overlap in time, okay? As can be seen in the example where we have 3 processes and all of them plotted against the CPU time. Process A and B and A and C are said to be concurrent because their instruction execution or flow of execution are overlapped in time. If otherwise, then the processes are sequential. B and C are sequential because C starts only after process B ends. So this is what concurrency means. Okay, and how does the user views this? The user view of the concurrent processes is as if they are actually running at the same time. That's the illusion that they have, that they are in full control of the CPU, when in reality, the processes can get paused, but still conceptually executing, but not really, because they are not making use of the processor. However, we can think of concurrency or we can think of concurrent processes as executing in parallel. And how does that work with a single processor? There should be some mechanism that switches between these processes, which is called context switching. So the processes are managed by a shared chunk of operating system code called the kernel. And it is important to know that the kernel is not a separate process, but it is just a piece of code, a special piece of code that runs as a part of the user process. But kernel code has special privileges. So this is how a context switch happens. Say that that the process A is running and suddenly it is time based on a timer interrupt, which says that CPU time for process A is up. So now here we have a timer interrupt that switches to the kernel code. The kernel will save the state of process A and restore the state of process B. Then process B runs until interrupted by the kernel, and then the kernel code executes and saves process B here and restores the state of the process A here. This is actually what is meant by context switching. Let us go a little bit deeper into what actually is the context switch. Recall the registers of x86 architecture, which has different registers to address the various segments of the main memory. This is our main memory. We have CS, the code segment that is addressed using the EIP, extended instruction pointer. We have the stack, the SS, the stack segment that is addressed by the ESP and EBP, right? And then we have DS, the data segment, and the extended segment, ES, and of course, all the rest of the registers that are used for a broad range of computation, okay? So this is known as the address space of the process. And the process is allocated an address space that includes the code section, stack section, and data sections. But we have many programs running in our computers at the same time, in which case they all need the CPU time to execute their instructions, right? But the problem is that we only have one set of these registers. This is where context switch plays the trick. So context switching is about sharing the CPU time. So here we have a user process, and let's suppose that this is the state of the process before the interrupt occurred. In the context switch, we need to save the instruction pointer because we need to know where process A stopped. So we can jump to that address location in the code segment of memory and continue executing process A. In the same breath, we also need to save the state of the ESP that addresses the stack segment of the memory. And besides that, we also need to save the E flag register and all other registers, because we will need to restore the data that will be required by process A. There are also other things to keep track of. However, we want to make the list short in the video for good understanding. So watch carefully what happens during the context switch. This is our kernel process, and in the context switch, the kernel code takes the charge and stores the state of process A at that instance, and similarly restores the status of process B, and process B get alive now. So this is what is meant by context switching. Now we will talk about some system calls through which these processes are managed. We are going to use a model called Fork-Exec model. Fork creates a copy of the current process, and the exec-v replaces the current process code and its address space with the code for a different program. So note that this is the Linux. So these are the system calls. So note that this is the Linux model of managing processes. Windows are slightly different, but the concepts are essentially the same. Other system calls for process management includes get PID, exit, wait, and wait PID. That we will see shortly. So let us see fork in action. Fork is used to create new processes. When you call a fork, it takes no parameters and it returns the PID, that is the process ID. So fork creates a new process that is identical to the calling process, that is the parent process. It returns 0 to the child process and it returns the child process ID to the parent process. It might be a little bit confusing. The reason is that it is called once and returns twice, right? Let us understand the concept of fork system call. Let us say we have a process N and it calls the fork method. It is going to create a child process called M and they return the same program, right? As we said, that fork creates an entire replica of the calling process, byte by byte, okay? And the entire state, because now they are running at the same time. The process continues to execute and it receives the PID is equal to M, which is the PID of the child process. And the child process is running and it is going to receive 0. Now, since a process N received M, it is going to execute the else part of the code. And process M will execute the if part of the code. And you will see a hello from the child. Okay, that should be simple. Which one executes first? Well, we only know that the process N started first. And after the child process is created, we really don't know which one will execute first. So this is an example of fork to highlight certain things. So we know that the parent and child both run the same code. The child is distinguished by the value it received from the fork system call, and which runs first is undefined. One thing to notice that though both processes start with the same state, but each has a private copy of the state. Same variables, same call stack, same file descriptors, same register contents, even the same program counter. So now that we know what our processes and how are they created, let us see how can we use Fork-Exec model to do some interesting things. As we know that the fork method creates an identical copy of the calling process with the same code and address space. The exec model, the exec-v system call replaces the current code and address space with the code for a different program. This is there is a whole family of exec calls, and I encourage you all to explore it yourself. Let us briefly look into this example. So we said that the process calls a fork to create a new process. If the PID is not equal to 0, that's the parent created a child. And if the PID is 0, that's the child. And when we run the exec-v, now it is running a program. Now it is running a new program at location indicated by the path and indicated by the path with the list of parameters. This is a very high level diagram of what happens when you run what happens when we run the command ls in a Linux shell. Ls is the listing command in Linux, similar to the directory command dir in Windows. We run the ls command in the bash command line. In reality, what happens is that bash program actually forks the system using the fork system call, in response to which a child is created that is a copy of its parents. Now, it needs to exec the system for replacing the address space and the code with the address space and code for the ls program. That is going to list the directory for you. Okay, so long story short, bash is also a process, and for ls it is going to create a new process, and it is going to replace the child process with the code and address space of ls, because ls is also just a program. Let's look at how Exec-ing works in a bit more detail. Here we have the Exec-ing function that basically loads and runs the current process. It takes three parameters: the file name of the executable containing the program we want to execute, the argument v has the arguments that we want to pass into the function, and the nvp is the environment list. Okay, now note that the exec-v does not return. It only returns when there is an error. This is because when exec-v is called, it was running in another program, and now it is running in another process, and it is no longer running in the calling process. Okay, so that's why it does not return. And as we said before, that it overrides the code, the data, and the state. It keeps certain things intact, such as the PID, open files, and a few other things. So the actual data structure looks something like this. This is the stack frame of our main function. We have the argument count. This is the argument vector that points to a vector that is a list of pointers, which further points to the command line arguments. And here is the environment path that also points to another vector that further points to the contents of environable variable. So what are the command line strings? These are command line strings. Okay, it could be a present working directory, it could be a file name, directory name, it could be another program, etc. Now, how are we going to end a process? We use the exit function. It returns a parameter that is the status to inform why the process exit. The status 0 indicates a normal exit, and a non-zero value indicates an abnormal exit. You can also call the function @exit if you want to perform something before the process exits. Okay, for example, you want to do some cleanup before you exit the process, but it does not really destroys the process. So that is what creates zombie processes, because when a process terminates, it still consumes resources, including various tables maintained by the operating system. These zombies needs to be removed, right? So there is a process called reaping that is performed by the parents on terminated child, and the parent is given an exit status, and the reaping process tells the kernel to discard whatever is left from that process. What if a parent does not reap? Well, that could be a problem, but thanks to the init process, that is the parent process of all the processes. However, in long-running processes such as the shells and servers, we need to explicit reap. Now we know how our process is created and what happens when processes are terminated. Let's talk about synchronization with children processes. There is a function called wait that is used to synchronize between children processes. When you call wait, it suspends the current process, that is the parent process, until one of its child terminates, and the return value is that of the terminated child, and it will be reaped. If the parent process has multiple children, wait will return when any of the children terminates. The wait PID can be used to wait on a specific child process, okay? To summarize, we talked about processes. We learned a very important abstraction that has enabled the concept of multitasking. However, since we have only one CPU with one register file that can process the instructions of only one program. Therefore, we need to share CPU time among these processes in a way that gives the user processes an illusion that the CPU is exclusively being used by them. This is achieved through context switching between active processes using the concept of exceptional control flow. We also talked about process management. Fork gets us 2 copies of the same process but returns twice. Returns a non-zero value to the parent process and 0 value to the child process. Exec-V then replaces the address space with the code and other requirements of the new program. The wait call is used to synchronize among multiple processes of a program, multiple children processes of a program. Then we also have the wait PID that is used to wait on a specific child to terminate. The exit call is used to terminate a child process, and it has no return. In the next video, we talk about process control block, which is an important data structure that is maintained by the operating system for process management.